Welcome to The Explainer. Today we are tackling one of the most mind-bending ideas in all of physics, quantum entanglement. It's a concept so strange, it really bothered Albert Einstein.
So, let's kick things off with a puzzle that perplexed some of the greatest scientists of the last century. Just imagine, what if you had two particles that were perfectly connected, linked by some kind of invisible thread? So perfectly linked that if you measured one, you'd instantly know something about the other, even if it was on the other side of the galaxy.
Yeah, this idea seemed so bizarre, so much like magic instead of science, that it deeply troubled Albert Einstein. He was convinced it had to be wrong, that it violated the ultimate speed limit of the universe, the speed of light. And he gave it that famous and kind of dismissive nickname, spooky action at a distance.
Okay, so what exactly is this connection that Einstein found so spooky? And why does it seem to just shatter our everyday, common-sense idea of how the world is supposed to work? Let's break it down.
You know, in the simplest terms, quantum entanglement just means that particles can stop being individuals and become part of a single, unified system. They're so fundamentally connected that measuring one has an immediate, and I mean instantaneous, effect on the other, no matter how much space is between them.
Now, I know what you might be thinking. Hold on, that doesn't sound that strange. And you're not alone. The physicist John Bell used this really clever analogy about his colleague, a guy named Dr. Bertelsmann, who apparently always wore mismatched socks. So if you see one of his socks is pink, you instantly know the other one isn't. But that's just a classical correlation. You're just discovering information that was already there all along.
And this right here is the quantum leap we have to take. With the socks, their color was set in stone the moment Bertelsmann got dressed. But with entangled particles, their properties, like, say, their spin, are genuinely undecided until the exact moment you measure them. It's not that we just don't know the state. The state itself doesn't exist in a definite way until we look. That's the spooky part.
So this fundamental weirdness, this idea that properties are sort of created by the act of observation, well, that's what led Einstein to formally challenge the very foundations of quantum mechanics in one of the most famous thought experiments of all time.
He got together with his colleagues Podolsky and Rosen, and they published what we now call the EPR paradox. Their argument was pretty elegant. If this instantaneous connection was real, then the theory of quantum mechanics itself must be incomplete. It had to be missing something.
At the core of Einstein's whole objection was a worldview called local realism. And honestly, this is basically just common sense. First, things have definite properties even when we aren't looking at them. And second, nothing can travel faster than light. So he proposed that there must be some hidden variables, like secret instructions that each particle carries with it, that predetermine the outcome of any measurement. No spookiness required.
For nearly 30 years, this was just a philosophical argument. You had Einstein's hidden variables on one side and quantum uncertainty on the other. There was just no way to know who was right, until a physicist named John Bell came up with an absolutely brilliant idea to actually put reality to the test.
Bell created a theorem, this inequality, that acted like a referee. If Einstein's local realism and his hidden variables were correct, the results of certain experiments would have to stay below a very specific statistical limit. But, and this is the key, if quantum mechanics and its spooky connection were correct, that limit would be broken.
Bell's paper basically fired the starting gun on a decades-long scientific quest. You had John Clauser running the first real experimental tests in the 70s, then Alan Aspect followed up with even more precise experiments in the 80s, trying to close every possible loophole to get a final, definitive answer.
So, after all the debate, all the thought experiments, and all the real-world tests, what was the outcome? Is the universe the sort of common-sense, orderly place Einstein believed it was, or is it fundamentally spooky? Well, the verdict came back, and it was stunning. In experiment after experiment, each one with more and more precision, the results consistently violated Bell's inequality. The universe, as it turns out, sided with quantum mechanics. Reality is not local.
What's really remarkable is just how clear the results are. In these tests, if the universe followed Einstein's common sense rules, the statistical result could never go above 2. But quantum mechanics predicted it could. And look at this 2017 experiment, just one of many, which found a value of 2.37. That's a clear, decisive victory for quantum spookiness.
And in 2022, this incredible achievement was finally recognized with the Nobel Prize in Physics. It was awarded to Aspect, Clauser, and Anton Zeilinger for their pioneering experiments that settled the debate,
proved Einstein's intuition wrong, and really opened the door to a new technological revolution.
Right, because this isn't just some quirky feature of reality. By learning how to harness this spooky action, scientists and engineers are now building technologies that were once purely the stuff of science fiction.
Take quantum teleportation, for instance. Now, this isn't about beaming people across space like in Star Trek. It's about transferring quantum information. By using an entangled pair, you can recreate the exact quantum state of a particle at a distant location, which effectively teleports the information it holds, without it ever physically crossing the space in between. It's wild. And that is really just the beginning. Entanglement is the engine behind quantum computers that are poised to solve problems that are way beyond the reach of even our best supercomputers. It's the foundation for creating perfectly secure, unhackable communication channels, and it's even helping us build sensors with just unimaginable precision.
So what started as a paradox, a spooky flaw that Einstein thought would unravel quantum theory, has now been proven to be a fundamental feature of our reality. It's become the cornerstone of next-generation technology, and it leaves us with this really tantalizing thought. If our universe is this weird and this interconnected, what other incredible secrets are just waiting to be discovered?